Hello, this is Dr. Christy Patton Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be continuing looking at reactor design for our process design course. We are doing this based on the textbook by Turton et al. So in this lesson, we want to consider what do we need to do to produce a desired product when there are multiple products possible. So one of the things that we need to always consider, is what conditions can I change that will improve my selectivity or my yield or my overall conversion. So we can generally control temperature and pressure. We can control whether or not we have a reactor that mixes or more like a plug flow reactor. And we can control what we are feeding to the reactor to some extent. So how each one of these is going to actually affect the reaction or the reactor process is going to depend on the reaction kinetics. So the first rule, and you should have covered these in a reactor design class, so none of this should be new, but it's a refresher. So the first rule is that high temperature favors the reaction with the larger activation energy, right? That's the exponent or the numerator and the exponent portion of the reaction rate. Low temperature is going to favor the one with the lower activation energy. But temperature doesn't have any effect on the rates of the competing reactions when the activation energies are the same. The second rule is concentration. So high concentration is going to favor the reaction that has a higher reaction order for C sub A. WRT is with respect to. Low Ca is going to favor the reaction with the lower reaction order. And if they both are the same, then it's not going to have any effect. Rule 3 is about when you have an intermediate product. If you're wanting to maximize the amount of R in a reaction, where R is going to leave and move into being S if you don't, control things, you can get the highest concentration of R if you don't allow fluids with different ratios of A and R to mix. So that generally says that you're going to want to use a plug flow style reactor rather than a mixed flow or C-star tank reactor. Generally, we'll also do better if we operate at low conversions. When we have combined reactions, try to analyze them in terms of their constituent series reactions or parallel reactions. It's easy to understand what to do with A going to R, which then makes S. And it's easy to understand what B going to R or S will do. It's complicated to analyze what happens with A plus B making R and R plus B making S. So breaking them apart into these series and parallel steps makes it much more easy to figure out what you should do. So let's look at a couple of examples here. So the first one is what conditions will favor the formation of maximizing R. So we have reaction rate 1 and reaction rate 2 given here. And for maximizing R, we want reaction rate 1 to be faster. The activation energy for 1 is higher, so therefore we would like to operate at a high temperature. As far as concentrations, it looks like C sub A has the higher order with reaction 1, so we would like high concentration of A, and low concentration of B, because concentration of B is higher for reaction 2. Here's another one, A making R making S. Now the activation energies are the same for both of those, so temperature is not going to affect this. And then we have C sub A and C sub R squared. So In this one, we want to do a plug flow reactor. It doesn't matter what our choice of temperature is, and we'd like to minimize the concentration of R, so we would like to remove it or have a low conversion in order to minimize the formation of S. And finally, let's look at this acrylic acid process. Here we have a set of 3 different reactions here, okay, with our various information given over here. Reaction 2 has the highest activation energy, so we are wanting to make acrylic acid, which is reaction 1, which is the lowest activation energy. So therefore, low temperature would be our desired temperature. And then we have that these are all basically of the form propylene plus oxygen. And we would like to probably have a feed where you have less oxygen based on the stoichiometry, because it's going to take up more oxygen to make acetic acid or CO2. And so we would like to minimize those. So these are the sorts of things that you should always consider when you're designing your reactor scheme in order to create the most of your desired product. We are going to be looking at more of the details of how we can optimally design our reactor scheme in the next video lesson. Thank you very much for your time.